This program is a presentation of UCTV for educational and non-commercial use only.
Good morning. I'm Heeger. I'm going to tell you a little bit about the recent effort within the this EFRC grant that the university, or that this institute, Institute for Energy Efficiency, received from the Department of Energy. We were very pleased to learn a few weeks ago that we were among a relatively small group of institutions that were winners in this competition. We received here approximately, or we will receive over the next few years, approximately 19 million in this program from the Department of Energy. It consists of many different programs, one of which is this focus on next generation solar cells. As you probably know, conversion of sunlight into electricity is a very attractive way to create energy, to create electricity. It's a known method. It's been around for about 50 years. I have solar cells on my rooftop. My electric bill is zero. Most of the time during the day, my meter runs backwards. And it gives me a great deal of pleasure to get that electric bill every month and find that I generated slightly more than I used. But the problem, I think you all know, is that it's not competitively priced. The cost of this generation of electricity from the sun is too high. There's plenty of energy coming down at us. Usual phrase is that in 1 hour, we receive on the Earth enough energy to supply all the energy needs of the inhabitants of the Earth for a whole year. Okay? That's a factor of 10,000 or something like that. So there's plenty of energy. The issue is, can we get it efficiently? Can we do this conversion with sufficiently high efficiency, and can we generate enough area of these solar cells to be able to make that a significant contribution to our energy needs? We get on the surface of the Earth, outside now, approximately 1 kilowatt for every square meter. Okay, that's what's coming down. That's 1/10 of a watt, 100 milliwatts on a square centimeter. But think of a kilowatt, think of a square meter. So you sort of know on your house how big that is. And you also know that a light bulb or something is going to require something like 100 watts. If you have 10% efficient solar cell and you have a 1 kilowatt per square meter, then 1 square meter is more or less capable of one light bulb, lighting one light bulb. And you know, I'm being very approximate in my numbers. So that means clearly that in order to have a significant contribution from conversion of sunlight into electricity, one needs a lot of area. Okay? So we need to have technology. We need to develop technology which will be low cost and that is capable of a lot of area. Low cost so that it's competitive with fossil burning fuel-driven turbines for electricity. The solar cell photovoltaic effort within this Department of Energy grant to the Institute has three components. One component is based on low-cost plastic solar cells. They look something like that. They look like this. Here's an example. This is a 2-watt plastic lightweight solar cell. Now, I'll spend a little time talking about this technology because it's the technology that I'm fully committed to. But there's a group of us here who are working on the materials that go into it, the precise nanoscale morphology that is required to make it work and work well, and the evaluation, if you like, of the technology. A strong group, this proposal, when I read it after it was completed, I had the feeling it was a good proposal, but that what would sell it was the strength of the team. And I honestly think that's what happened. I mean, we really have an outstanding group of people in each of these areas, and I'm quite confident that that's why we were successful in attracting these funds. Another area is indium gallium nitride-based solar cells. I'm not going to say very much about this, except to comment that there has been traditionally for 30 years at UC Santa Barbara strength and a focus on compound semiconductors that goes back to Herb Kromer in the 70s. That strength remains. Many of these names are familiar to you, and you've met or you heard, I think, Steve Denbar's, Suji Nakamura, John Bowers, these people you know. So again, a very strong group, a group that carries the kind of weight to attract this kind of funding. And the third area is quite interesting and novel. These are nanostructured and bio-inspired photovoltaic materials. Galen Stuckey here is a chemist who is famous for creating nanoscale structures. Dan Morse is focused on this effort. This is a little farther out, but very interesting with interesting potential. So let me go back to this and just tell you a little bit about this approach that I'm involved with and my colleagues. The idea here is that we're going to take a new kind of semiconductor, semiconductors which are polymers, which are plastics, and those plastics can be dissolved in common solvents, and because they can be dissolved in common solvents, they can be formulated as inks, and we can print them, or we can coat with them. So the methodology here is to actually use roll-to-roll coating to create solar cells that look something like this, okay? And if you use plastic substrates and very thin materials, and it's all plastic, then it's bendable, it's very lightweight, and as you'll see in a moment, capable of generating very large area. Now, The initial discoveries which opened this field were done here in my labs in the 1990s. And we had the audacity to start a company in 2001. The company is called Kanaka, and it's in Lowell, Massachusetts, near Boston. And here's recently a facility that that has been manufacturing, that's the proper word, roll-to-roll manufacturing of these flexible plastic solar cells. You can see here that is a plastic roll which generates something about this size. But the point is, this is analogous to a printing press. In many ways simpler because we're just putting more or less uniform coating on. It can go fast, and it can generate a lot of area, and it works. And what happens is you generate the first layer, you put the first layer of material here that runs all the way down to the end. The roll comes down, around, up, and back to the second area, and then the other way to the third, and the fourth, and the fifth. So you can put a multi-layer structure together like this, and out the end comes a solar cell. Printing is perhaps the lowest cost manufacturing that one can imagine. So the idea here is to create large areas and low cost with this novel technology. Now, this really works. I mean, of course, this isn't what we're doing here at the university. This is built upon work that we and others did in universities, but made that step, made the investments to commercialize the technology. Just one little comment. This is about a $250 million facility, but it was acquired for less than $5 million because it was a Polaroid roll-to-roll manufacturing plant for photographic film. They needed multi-layer films, and the plant could not have been better designed for our needs. Now, if you think about that a moment, Kodak is no longer selling film, and Fuji is no longer selling film. So there's capability of this kind around. And so if the efficiency can be made high enough, this could be ramped up to very large scale in a relatively short time without even a very major capital investment. So let me say a word about efficiency. The problem that we're dealing with, this is real. Okay, I carry this around, carry it in my suitcase, take it through airports, it gets beat up, but it works. Okay, right now here, even indoors, this little meter is putting out 3.5 volts. That's the open circuit voltage. I won't get into the details, but this is real. The problem is that the efficiency is not high enough. Okay, the cost is inversely proportional to the efficiency and to the lifetime. If you have a very high efficiency, then cost is going to go down in dollars per kilowatt hour. If the device only lives for a year, then all your manufacturing costs have to be taken out in a year. If it lives for 10 years, cost in dollars per kilowatt hour goes down. So we need to improve the efficiency, we need to improve the lifetime, and that involves basic science, chemistry, synthesis, material science, device science, and that's what we're doing here at the university. Efficiency can be written as this product. We need to collect our more photons and get a higher short circuit current. We need to have materials which have absorption spectra that are better matched to the solar spectrum. We need to have a deeper understanding of the origin of the open circuit voltage and how to manipulate the materials so that we can optimize that. And these are materials that are synthesized by chemists. So we can, if we understand this deeply enough, we can actually make what we need and put it all together. So there's a synthesis component here. Colleagues who are making, Fred Woodle, Guy Bazan, who are making new polymers, new acceptors, with the goal of using really molecular design of new materials for efficient harvesting of the photons from the sun. We're getting to the point where we can write down molecular structures, invent them, create them, and then some of us can actually cook them, make them, and then we can begin to use them in these kinds of applications. It's more complicated than that. I don't have time to go into it, but there's a very significant material science aspect to this. The whole concept is based on spontaneous phase separation. One has to control that phase separation. One needs to control the structure, the nanostructure, the packing of the materials. There's a high level of complexity here, and sometimes in the middle of the night I wonder why it works at all. But it does, and we're doing very well. But the goal here is to optimize this nanoscale morphology for separating the charge and for collecting the charge. And there, again, is a group of people here who have established themselves as expert in this area and who are carrying that load. And then finally, obviously one has to really make the solar cells from the materials, try to optimize, get the device science right with the goal of high efficiency and long lifetime. Each of these last three slides involves, behind the scenes, of course, a great deal of science, a great deal of scientific challenge. So the question, I guess, is it worth it? Okay, and I tried just in a one-liner here to lay out the potential impact. We know, we pretty much know the cost of goods, the cost that it required to produce this kind of a solar cell. And we have a good idea of what the installation costs would be. So we can make a pretty good guesstimate of what the electricity would cost if this technology really goes. The cost of conversion of sunlight to electricity. So this number, which is, by the way, obviously a very attractive number, would be approximately the right number if we had devices with 8% efficiency and a lifetime of 8 years. Okay? We're going to be able to do that. I'm really confident of that. We have in our labs today a 6% efficiency, and there have been experiments at Kanaka which have already shown that one can get to several years of lifetime. So I'm pretty optimistic that we can do that. If you just play with me for a second, if you go up to 12 years, 12% and 12 years lifetime, that's another factor of 2 reduction. And now we're talking about literally a few cents per kilowatt hour. At that point, the cost of the solar cells will be significantly less than the electronics, the inverter that you need to convert the DC into the AC. So there's a potential here of major impact if we can in fact realize these goals. I said I was confident. We're seeing the kinds of materials. We know what we need to do, and we're seeing these materials. We're realizing these materials in our laboratories here and from our colleagues elsewhere. So I think we're going to see this come true. I'll stop there. Be glad to answer questions. I guess I should show the last slide. Okay, so that's my house. That's my solar cells. Okay, what I like to do is take off those big, bulky, expensive silicon solar cells and replace them with this plastic stuff, and hopefully, even one day, have the plastic solar cell integrated into the roofing tile. So when you install the roof, you install the photovoltaics. But, you know, you have to dream. Questions? Yes?
I come from the solar industry. I was an installer for a number of years. And my question has to do with the environmental impact of the manufacture of these things. And I was at the McDonough lecture last night. And my question is, using his cradle-to-cradle approach to raw materials used, manufacture, et cetera, which of the PV technologies is or can become the most...
Wait, too many things, one thing at a time. Environmental impact, let's talk about that.
Let me finish the question and it'll become clear.
Okay.
Which of the PV technologies is the most appropriate from an environmental impact approach? This is a question that I'm asked constantly by customers. Is this really clean, or is it ultimately a dirty product?
Clean. I mean, we use solvents. We cast the films from solution, but the solvents are all handled right on site with a very efficient means of taking care of. There's no emissions. The substrate is a standard PET plastic substrate. That's actually reusable, recyclable. The active material, the colored stuff that you see on this demo, is very thin, only about 100 nanometers thick. Okay, so if I had a gallon jug of the solution, it'll cover Santa Barbara or something. I mean, so it's very thin. I don't think there's significant. These are non-toxic materials. There's no heavy metal in them. This is carbon and hydrogen with a little sulfur. So I think we're okay.
Thank
Yes?
you. I'm sorry, we don't have time for any more questions.
Okay.
We just
Sorry.
have to move on. If everybody can join me in thanking Professor. Introduce Jean-Marie.
Yes. Where is he? Aha. So our next speaker is Jean-Marie Tarason. He's just joined us here at UC Santa Barbara, having come previously from the Bell Telephone Labs and then several years in France. And we attracted him to California. His expertise is in the general area of electrochemistry, with a particular interest in energy storage through batteries. Jean-Marie? Oh, you have.
Okay, thanks, Alan, and thanks, John, for inviting me to come here and to give you a kind of overview, I will say, about the lithium-ion battery. And I have a difficult task because everyone hates batteries and complains about batteries. But I will try to show you more or less how the underlying science is very related to what's going on inside the Institute of Energy Efficiency. So why do we work first on this battery? And you are going to find the same issues that people have been talking for the last day, where we try to develop a new sustainable technology to better manage our renewable energy sources, maybe to couple with photovoltaics that Alan just mentioned to you, and also to favor the development of electric transportation. As you know, we want to shift from thermal to electric vehicles. Since as a thermal, when you are burning 1 liter of gasoline, you are daily delivering 1.5 kilograms of CO2, which is about 750 liters. So in this kind of application, what you want to store energy and to restitute as electricity. In order to do this, we are going to use the conversion of chemical energy into electricity. Why? Because both are using the same carrier that is the electron. So here more or less the type of batteries. And here I would like to put something very straight, because I was very frustrated yesterday and so on when everyone is showing some kind of forecast about factor 10 logarithmic scale. Let me compare that the work of battery is not a work of microelectronics. And in order to do so, I would like to use this transparency in order to make the difference between energy storage and memory storage. And this graph, as you can see, I am using log scale. And you can see, and you know this better than me, that the progress has been huge on the field of microelectronics, where the number of actions per chip has been increased by 50,000 in 30 years, or about 50 million number of megabits. Now, I am going to put more or less our progress in the field of batteries. So you can see we are following a Moore law, but not the same one. Okay? We are talking here about 2 times every 50 years. So please, don't be tough with us. But unfortunately, the press has not been very kind to us, because this is what you look on the field, on the press, looking at batteries. You can read it. I will just read the last one, because it's really the most interesting one. Our research in the field moves at a glacier pace. So they see more or less in the kind of environment that I am coming here. So let me tell you more or less now more details. What are the challenges and what needs to be done? So if you look in the field of batteries, this is more or less the different technologies that you have by now. You know all of them, and out of this one, the lithium-ion technology is, of course, the most attractive one, and which has been, I would say, the greatest advance of this last century. Now, how this technology that you all have in your laptops and your computer does work, very simple, as indicated here. You have these 2 famous electrodes, lithium carbon oxide and graphite, which are type of materials that are going to uptake and release lithium. I will not go into details, but the bottom line here, this is more or less what is going to control the longer the time that you will have to talk, which is more or less the gravimetric capacity, which is given by this simple formula. So, for quite a long time, people have been working in the field for 25 years and have defined kind of general rules. Turn out that after 25 years, the reason why we have this low progress, we end up to have these type of materials, which you have in your cell today, but you can see we are still limited. We have an intrinsic limitation. So back to 2000, and our team, we decide, in this case, to add the size as an additional variable to composition and structure in order to see if we can promote some better capacity and so on. And what we found, in this kind of passage toward nanomaterials, will come out with completely new, different mechanism, as indicated here, that we call conversion reaction. But just here, what you have to keep in mind, that by going to nanomaterials, we can get a factor of 3 improvements. And also, some compounds, some stones that didn't have any conducting electron and so on, can be turned into attractive interstitial materials, which has already led to some products. And everyone knows the success stories of A123 in the States and developing lithium iron phosphate. So this has recent advance at the nanomaterial scale. So today, this is where we are. The lithium-ion batteries are, as indicated here, powering most of the electronic market. And owing to the arrival of nanomaterials, we can now reach about 210 watt-hour per kilogram and 600 watt-hour per liter. Of course, now the main question is what we could do about automotive transportation. And here, bigger challenges do arrive. Indeed, what are they? First, you want to increase energy density, always the same, and of course, as always, lower the cost. And you want to do it by a factor 2 at least in terms of energy density, and decrease the cost by a factor 5. In order that you can go from $500 per kilowatt hour to about $100. Of course, what is very important is safety. And unfortunately, safety and cost are changing as opposite. If you want to increase safety, automatically you increase cost and vice versa. And last, and certainly one of the most important by now, is the material processes having the minimum environmental footprint. And you need to realize how we are making battery nowadays. This is more or less a cycle of batteries, where usually you pick up elements from the ground, you need to do extraction, purification, fabrication, and this stuff is going to be costly in energy in terms of CO2. Then since we are going to increase the amount of battery, as indicated here, you are obliged, and it's going to become mandatory to recycle. And this stuff is not easy, but you need to do it, all these kind of techniques here, which is again going to cost high CO2 impact. And last but not least, you need to have enough chemical elements. And everyone knows that our technology today is based on cobalt, and we are kind of becoming short on cobalt. So, the main message of all this stuff, it is urgent to consider electrode materials having the lowest possible cycle life cost and minimum environmental footprint. Why? Because we ask our car industry today, we need to shift from fossil fuel to batteries. Now, there is no way that we can ask them 15 years from now, guys, too bad, we give you batteries, but we don't have enough materials. So we need to think about what will be the next generation of materials. So what will be the ideal situation if you are dreaming? The ideal situation will be the following one. You could start from material coming from biomass, doing all types of processes at room temperature, what we call green chemistry. Then you can recycle, and you can see the CO2 is coming back. Of course, this is more or less the type of research that we have launched, and I'm going to show you several directions that we are pursuing along that line. We are going to see how we are moving to try to find inorganic materials that are abundant, and more importantly also, how we are going to make them in order to have a kind of eco-efficiency process. We are going to see the use of organic as a renewable lithium-ion insertion electrode, and I will show you how we can do this. And finally also, what's interesting is going back to some very old systems and with what we have learned about nanomaterials, how we can really use them. So if I look in the case of what are the trends here in terms of electrode materials, this is, for instance, a famous lithium phosphate that is most praised material nowadays in the lithium technology, which is a mineral and which was disregarded 20 years ago because of its poor electronic and conductivity. So in this case, you can see that we cannot use this material as made, but we need really to transform to nanomaterials. And of course, what is very important as a chemist is to find the best way to expedite and to find very low-cost processes. And what we have been doing and what we are doing, we play with all our chemistry knowledge in order to develop different techniques, as indicated here, when we move from the classical ceramic process to some low-temperature techniques, solution techniques, during which we both have an economy of atoms and also we decrease temperature. So we have kind of eco-efficient process. Of course, I am not going to detail some of this stuff, but still, there is one remark that I want to make, is the last approach here, which is bio-mineralization, and this will fit very nicely with what Alan mentioned previously and what is going on at the Institute, where some people are doing bio-mineralization. And what we try to do and what we have achieved is to synthesize the materials, as indicated here, by using here this bacteria that is going to force hydrolysis of our urea in our materials. To make the story short, you can do this, and as you see in this nice isolation electron microscopy picture, you can obtain needles of very nanoparticles of the lithium iron phosphate. So of course, this is just the beginning, but there is a large amount of materials that can be made using these processes, and here I make a list of all types of materials that we are targeting nowadays. Now this is a question regarding the nanomaterial approach. Now the question is, what will we gain by moving from inorganic to organic compounds, and again here, moving to the field that Alan Heeger has mentioned previously. What we have looked here is really with a different concept of seeing if these organic compounds could insert lithium. And interesting, we went to this kind of old chemistry, the oxocarbon, because for the side story, as a matter of fact, the first compound that has been ever made by man was a potassium croconate that has been made about the 18th centuries. We look at this compound, which contains here this carboxyl function. And when you look at these materials, you find that they can't really insert lithium. And of course, if you make a new compound, you want to claim something good, you need to do some benchmarking. And when we do some benchmarking with the famous compounds that we have today, which has lithium cobalt oxide and lithium iron phosphate that are our benchmark, you can see that this organic molecule, and it can perform very nicely with a huge increase in energy density. Of course, if you put this and the kind of volumetric density, owing to the fact that the polymers are light compared to inorganic compounds, here the advantage is somewhat decreased. But still, up to 1 C rate, which means in this case you can use this power in 1 hour, you can have nice performances. But the most spectacular result is the fact that these compounds can be made from natural resources. This is a molecule that we are using. This molecule can be made via some kind of chemical reaction from some kind of carbohydrate. And this carbohydrate, as indicated here, can be obtained from this kind of phytic acid, which is really a byproduct or product that you can find and which is distributed in a lot of plants and, for instance, constitute 8% of the dry weight of corn syrup liquor. So which means that we can really go from biomass to active electrode materials. And of course, people complain that polymers don't hold high temperature. This is more or less what we have achieved recently, where we can go up to 300 degrees C, and we have a perfect performances with nice rate. And not more than 1 month ago, we have realized what we call the first renewable organic lithium-ion cell, which in this case has the behavior indicated here. Of course, people can criticize very strongly since the potential is relatively small and so on, but this needs to be improved. The purpose of this slide was simply to give you the message that maybe we need to look at a new concept, a new way of designing batteries. And now you can really have the cycle process where you can take materials coming from the biomass, you can do some bioraffinery, fabrication, all this stuff can be done at very relatively low temperature, near room temperature. So definitively, there is a paradigm shift and present concept for improving the lithium-ion batteries. Now, of course, what is very important is that the gain by going to organics is not going to be in terms of performances. You will not make a battery that will perform better than nowadays lithium hydroxide carbon or lithium phosphate carbon. But the advantage is that you will use materials that are abundant and resource and so on. Now, if you want to increase the capacity while maintaining the sustainability and the green energy storage, now you may want to revisit what people have done on lithium-air batteries and so on. And here, I just want to show you some research that we have carried out now, where, again, this is all technology that everyone given up. Now, with all the learning that we have done on nanomaterials, we know how to nanostructure electrode and so on, which is the reason why such a battery that was used a long time ago as a primary battery now can be rechargeable. And what you look here is what we have achieved in terms of cycling. You can see we can get very nice cycling. Of course, if I show you only 4 cycles, it's because after 10 cycles, we cannot keep up the capacity. So we are still quite limited, but still it's quite promising. And of course, we have a huge amount of work in terms of electrode optimization, electrode porosity and so on, but of course, you need to realize that this is only 1/3 of the metal-air battery, since we have also to solve the electrolyte and the negative, which is the lithium issues, which is why research in the field of battery is relatively slow because we have a large amount of interfaces. So if you want to look, or if you want to have my outlook on the field of lithium-ion batteries, I should say this is more or less what we are today, where we talk about this conversion reaction electrode. The organic electrodes are somewhere here, the lithium air, and of course I put here some kind of thing that I am very interested is maybe now start to think also of other chemistries than lithium, since you have heard also of the limited supply or some limited supply lithium. But again, even in my crazy forecast, you can see I solely have a factor 2 here. So again, realize that the Moore law doesn't apply to our field of electrochemistry, unfortunately. And of course, I hope really that some of these technologies that I mentioned here can be really, or can use at least, the fundamental technology platform of the Institute to develop. And thank you for your attention. People want.
Anyone has one? No? Okay.
In an application where capacity is not the criteria, but the ability to recharge multiple times, or the cycle times to go up. What are the limitations in that, and is that something that is going to be improved from these green manufacturing processes?
Again, there is different topics. When you want to improve lifetime, you are going to work at the electrodes, and as additives you can put to the electrolyte and so on. So to increase the lifetime, we are going to select the right additive and modify the particles within the electrode materials in the way that we are binding the particle together. Because you need to realize that an electrode material, again, a complication, is not a single material, but is a formulation in which you have a binder, you have an electronic conductor, plus an active materials. And we need more or less to size the three components in order to design an electrode for either high density application or cycle life and so on. And the lithium air for sure can be long cycle life, but we need to make it cycle first.
Storage Group, Lon Bao, President and CEO of BSST, and he'll be talking on converting transportation and home HVAC systems to operate on renewable energy sources.
Thank you. I will try to go through some of the slides I had prepared a little bit fast in order to make up a little time for a town hall meeting. As we look at some of the new innovations in energy conservation, some of the things that happen are adverse events, and the adverse events need to be addressed in some fashion. In particular, when we have HVAC systems, these are heating, ventilation, air conditioning systems. Such systems, and the easiest example is in the car, now have alternate needs for power sources. Heating is no longer free. If we do not have the engine on, for example, in an electric vehicle, then what is the source of heat? If we have a hybrid vehicle where the engine is off during decelerations and stop, what is the source of heat? In these cases, then, we need to expend energy in a new way. We need to develop a source of heat. And then the question becomes, how can we do that efficiently, since in some cases, this is a brand new requirement. The solution in the automobile, for example, is to have a firebox or a heating source that's an alternative heater. This is used in Europe fairly extensively for small diesel engines, where it takes a very long time for the engine to heat up and provide heat. And it's inadequate in the winter and short commutes in much of Northern Europe. So in such systems, we maybe defeat some of the things that we are trying to accomplish as a society for the practical reality of providing something that causes people to buy vehicles, and that is comfort in the vehicle when it's cold. And so clearly a combustion heat source would not be a good choice, but it is the choice, and several million are sold a year in Europe today. An alternative is resistive heaters. Resistive heaters have the issue that they are very inefficient. They simply convert electric power directly into heat through Joule effect. This is a very thermodynamically inefficient process, and as a result, it is a process that is unacceptable as we try to improve system-level efficiency. So what are the alternatives? I'm going to talk about those alternatives, and I'm also going to spend a few moments talking about the analogy of this, the analog of this in the home, where heating takes on different meaning if we choose not to use fossil fuels. We have some options, and I'll talk about those options. The main thrust of what I want to talk about is a transformational technology, which is solid state, which is thermoelectrics, the conversion of electricity directly into some other form of power. For example, electricity into hot and cold, such as is done with the heat pump. And the reverse process. The reverse process is where heat and temperature gradient is converted into electric power. Thermoelectrics look attractive in some ways because they are electric powered devices. They are solid-state devices. They have no gaseous emissions. If we think of traditional air conditioners, we think of two-phase fluids in the past, not today. In the past, it has been freons. The present two-phase fluids have some environmental issues, although they're getting better. And certainly over time, CO2, for example, as a refrigerant would have rather minimal environmental impact issues. But nevertheless, they are mechanical systems, they leak, and they have certain deficiencies. Also, it is somewhat difficult over a broad temperature range to make them work in reverse, make them heat and cool. The thermoelectrics are a technology that is emerging and are described here. I'll stick primarily to cooling and heating. Basically, there are two semiconductor materials where the working fluid in the case of thermoelectrics, rather than some freon-like material, are simply electrons. And whole electron pairs are created at one surface. As they are created, energy is absorbed, and where the electron hole pairs combine, energy is given off. The result is pumping of energy from one surface to another. The reverse process, which I won't spend much time on, is creating electric power, where heat separates and creates a whole electron pair, and then at a lower temperature, the pair is combined again. Thermoelectric devices are typically formed into arrays. For example, here is an array that was produced here at Santa Barbara. It is for low temperature power generation, waste heat recovery, but the same technology is being developed for cooling and heating application. You can see a very large array of elements. Each of these then is a little solid-state heat engine, each pair of these. And this array has quite a number on it, 16 by 16 array, and this dimension's about 2 centimeters by 2 centimeters. So these devices are large arrays of solid-state heat engines then. Thermoelectric devices, as I mentioned, can cool and by reversing the electric current heat. So they are reversible in that sense also. And so they can provide both heating and cooling within a very simple solid-state package. That's very attractive. The heat that is created in the form of a heat pump, and it follows certain rules, Carnot cycle rules that allow the device to have a degree of efficiency that's measured in terms of a coefficient of performance. And that number, subject to second law of thermodynamics, can be up to a certain limit. But typically, for devices of this sort, it's the order of 1.5, 2 times the amount of electric power put in under normal operating circumstances. With better and more efficient thermoelectric materials, that number could be higher. And one of the serious problems with thermoelectrics is that the efficiency has not been high enough. And here at Santa Barbara and at other institutions, that is being worked on very aggressively, but there has not been much progress. It has been a long struggle. I'll talk very quickly about some of the approaches to increasing the efficiency. At Ohio State University, materials have gone from a level to about double what the materials were, and they have done so by improving a factor called the power factor. This term here is the figure of merit for a thermoelectric material. And they have improved the power factor. Our measurements validate their results. Similarly, at Michigan State University, they have made improvements in their case. They have reduced the thermal conductivity. Here at Santa Barbara, based on work done here and at University of California at Santa Cruz, they have combined the two and improved the power factor and improved the thermal conductivity. And the result has been even larger improvements. This is about an 80% improvement over conventional materials. So there is some signs that improvement can be made. One of the uses for thermoelectrics then is to provide heating and cooling. There are two problems with heating and cooling. One is the conversion efficiency, how much thermal power is created, and the second is the distribution problem. How do you get it to the occupant in the case of a car? And in this case, what we're doing is heating and cooling the seat of a car using thermoelectrics. Although the thermoelectric conversion efficiency is somewhat low, the efficiency of coupling it to the human is very, very high. And without going into details, it's about 50 times higher than the coupling efficiency to an occupant from the automobile's air conditioner itself. About 50 times, because much of the air in the air conditioner goes to heating the roof of the car, heating the back seat if no one's there, heating the floor, etc. So the coupling is much higher in this case, even though the device is less efficient. This leads to the concept of zonal heating and cooling, or regional heating or cooling, or heating and cooling on demand. And a solid-state device that can be distributed readily and has a very small natural size to the heat pump devices or the engines is very amenable to that. In a car, in heating, the amount of power that is used with resistive heating in a traditional car during startup is about 2 kilowatts. If we use zonal heating and use a thermoelectric heat pump, that number drops substantially to about 1/3. And so the result is that a substantial energy savings compared what it would have been with just resistive heating is possible. This partially then overcomes the deficiencies that arose because we eliminated a free waste heat source in the vehicle. If we just summarize very quickly and look at the home, and these are rough numbers, these are absolutely not precise, but hopefully they give a correct indication of the energy budgets with different energy sources. As we go from fossil fuels and we transport them to the home and we use a standard heating system to heat the home, we get about 900 watt hours of heating if we start with 1,000 watt hours of capacity from the energy source. If we take the same fossil fuel and combust it extremely efficiently, about as efficiently as we know how, and produce electricity from it, and then put it to the home and use it again with a thermoelectric now heat pump, then we get approximately 1,800 watts hours of heating. And so the heat pumping capability of the thermoelectric device boosts the amount by about a factor of 3. We could use other forms of heat pumps as well as the solid-state heat pumps and do slightly better or about the same. I don't mean to imply that this is the only possibility. But the very interesting thing is, if we now take a wind machine or some other solar form of energy production or hydroelectric that directly converts some form of renewable energy, and we have 1,000 watt hours produced, and we transport it into the home, then with a heat pump, we have about 2,500 watt-hours of heating. In cooling, the efficiency is not so attractive, and the thermoelectric would be less efficient than a standard two-phase refrigerant. Work at Santa Barbara here and elsewhere on better thermoelectric materials had the prospect of correcting that deficiency. If we had thermoelectric materials that are about twice as good as they are today, that difference would be eliminated. In some cases, it could even be a lower number. In the case of hybrid electric vehicles, for example, it needs to be about a 30% improvement to have parity for cooling. And in heating, there is a substantial gain. So the result is that we can, rather than use a fossil fuel and transport it and heat a home directly, and use the combustion process, which is traditionally done in a very inefficient way, if we substitute some form of a heat pump and we can use renewable energy source and put it on the grid, it becomes a very efficient way then to overcome this difficulty. Similarly, in an electrified vehicle, a hybrid, a plug-in hybrid, an electric vehicle, a pure electric vehicle, we can convert then electric power directly into the propulsion system and the energy management system of the vehicle, and achieve, again, the same type of ratio in efficiency gain compared with resistive heating. So both the technology has the prospect then of helping resolve some of the issues that are created by the desire to convert from fossil fuels to other power systems. The result is that some of our societal goals and the need for greenhouse gas emission reductions and CO2 emission reductions solve certain problems, creates others, and it creates opportunities for new technologies, in particular solid-state energy conversion technologies that might then be a significant contributor to the solution to the resultant problems. Thank you very much.